where we dealt with segment lengths or areas. In each type of problem, we are going to put our target segment or area and divide it by the entire segment or area every single time. Page 463, this is an example. We had a line segment from A to B. We were told that AC was equal to AB, which means that C is the midpoint. Now, all of these numbers weren't given to us, so we would simply assume that from A to B is 1 unit long. Or you could assign it a value, say as 20 or 8 or 12, whatever, and then break each thing down accordingly. Well, AC is half because C is the midpoint of AB, and half of 1 is 1. Here you see that CD is equal to DB, which means that D is the midpoint of CB. Since CB had a measure of 1/2 and CD is half of that, you get the measure of 1/4. If DB had a measure of 1/4 and E is the midpoint, then half of 1/4 is 1/8. And here's your other eighth. Okay? Questions will be asked such as this. If a point is randomly selected on segments AB, what is the probability that it will be located on segment AD? Well, the way we solve that probability is the length of segment AD, which is 1/2 plus 1/4. Remember, adding, you need a common denominator. And this gives you 3/4 divided by 1, because the entire segment is 1. Well, 3/4 divided by 1 is still 3/4. What is the probability that it would be located on segment DB? The entire length of DB is 1/4 divided by 1. What is the probability that it would be located on AB? 1, or 100%. Alright, if you're going to receive a phone call sometime between 4 and 5:30, and at 3:50 you have to leave for 45 minutes, what is the probability that you will miss the call? The probability that we will miss the call is equal to the total number of minutes during our allotted call time. So we're going to get the call between 4 and 5:30. If we have to leave at 3:50, that from 3:50 to 4 o'clock doesn't count. So if you're leaving for 45 minutes and 10 minutes doesn't count, then there are 35 minutes that you will not be home. And this needs to be divided by the total number of minutes where someone will be calling. Well, from 4 to 5:30 is 60 plus 30, or 90 minutes. And we would reduce that to lowest terms, which 5 goes into 35 7 times. I have a cramp in my foot. Ow! And 5 goes into 90 18 times. And so this would be our probability that we will miss the phone call. Now, the question could also be asked, what's the probability that you will get the phone call? In this case, we look at the total number of minutes that we will be home. Well, if we're going to be home, let's see, if we leave at 3:50, we just said 35 of our 90 minutes we would be away, so that means 55 out of our 90 minutes we will be home. And then we reduce that to lowest terms. And 5 goes into 55 11 times. And 5 goes into 90 18 times. So that is the probability. Okay, we also had this picture, and I can do all kinds of crazy stuff with it. I can ask you what's the probability that something will land in just one of these corners, in 2 of the corners, 3 of the corners, all 4 of the corners, just one of these sections, the inside square, all kinds of stuff. But for each thing, you need to know what's the measure of the side of the smaller triangle, what's the radius, and what's the measure of the side of the larger triangle. Okay, and I have this wrong. Let me fix this. This needs to be crooked. Like that. Okay. Alright. Well, since the square is inscribed in the circle, then we know that when we draw this diagonal from one corner to the other of the square, since this is a 90-degree angle right here, oops, hey, weren't supposed to move, then it creates a 45, 45, 90, in which the side of the square, which we don't have a number for, so we will simply assign a side length of 1. The leg is equal to, the hypotenuse is equal to the leg multiplied by the square root of 2. I don't think I have a radical symbol. Let's see. It doesn't finish it off for me, as you can see. So we'll just do this. All right. Now, because this inscribed angle is 90 degrees, then it is intercepting a 180-degree arc, which means that this dark red line is the diameter of my circle. So that allows me to find my radius. Also, because this is a square and it has been cut in half, then the square root of 2 is also the side length of the larger square. Square root of 2 divided by 2 let's just start over, would be the measure of your radius. Okie dokie. So your radius is equal to this. The length of the side of your small square is this, and the length of the side of your large square is this. Now, if I said, what is the probability that a dart thrown at this target will land in the square? You're going to take your target area, which would be the area of the square, the smaller square, and divide that by the total area of the entire target, so it would be the area of the large square. Now the area of the smaller square is side squared, or 1 times 1 for 1 squared, over, this is hard you guys, I'm trying, over the side of the larger square squared, and the square root of 2 squared is 2. Wow, say square one more time. And so that is your probability, which means basically that this inner square takes up half the area of the whole thing. Now, I could also ask you, what's the probability that the the thing will hit in the circle? Anywhere in the circle. I haven't said not in the middle square. I've simply said in the circle. So you would find the area of the circle and divide it by the area of the large square. And you can plug into those formulas yourself because it's going to take too long for me to type it. If I said, what's the probability that the darts will hit in these 4 corners? Well, you would start with the area of the large square and subtract out of it the area of the circle, and then divide by the whole target. I could ask you all kinds of crazy things, so be ready. And finally, you have a bullseye with a diameter of 5 centimeters sitting on a